we'll solve some problem in set theory or sets. So let's start from problem 1. So what is our problem 1? And this problem is mainly important in Calcutta University B.Sc course, mathematics honors. So let capital A and capital B and capital C denote three subsets of a set S, and C complement denote the complement of C prime denote the complement of the set C in the universal set S. S represent the universal set if A intersection C, this is equals to B intersection C, and A intersection C complement, this is equals to B intersection C complement. Then prove that B equals to A. So now how to solve this kind of problem? Here we'll solve this problem. So how to solve? What is exactly given? So it is given A and B and C are subset of the universal set S, subset of a set S, and the second information is C complement. This is basically complement of C in S, that means it is S minus C. And the third information is here A intersection C, this is equals to B intersection C, and A intersection C dash C complement, this is B intersection C complement. So what we have to prove? Here we have to prove that B equals to A. That we have to prove. So now we start from the set A. We can write A is basically A intersection S, where S is basically the universal set here. And from that we can write A intersection C union C complement. Why? Because C union C complement, this is basically universal set for any set A and its complement, and that union will be the universal set. So now we'll apply the distributive law, and from that we can write A intersection C union A intersection C complement, and this is by distributive law. Now what is the intersection C? This is basically B intersection C. So just we have, this is basically 1. So by 1 we can write intersection C as B intersection C union, and A intersection C complement, that we can write B intersection C complement, and this is by 1. Again we apply distributive law, and from that we can write B intersection C union C complement, again by distributive law. And from that we can write this is B intersection S, because C and C complement union C complement, this will be the universal set S. And if we take intersection of a set and the universal set, that will be exactly B. So what we have proved here, so therefore A equals to B, and this is our proof. So this completes the proof. Now we will go to the second problem, problem number 2, and this problem is important also, very very important. Let capital A, capital B and capital C the three sets such that A intersection B, this is equals to A intersection C, and A union B, this is also equals to A union C. Now, what is the question? Then prove that again B equals to C. How to solve this kind of problem? So now we come to the solution. What is exactly given? So it is given that A and B, comma C are three sets, and next information A intersection B equals to A intersection C, and A union B equals to A union C. And here we just consider S is basically universal set. Let S be the universal set. That is our consideration. Now what we have to prove? We have to prove that B equals to C. That we have to prove. Now how to prove B equals to C? So now start from the set B and we'll show it is basically C. So now start from the set B, and that we can write B union A intersection B, and this is just by absorptive law. Absorptive law. Okay, you can easily visualize with the help of Venn diagram. And here you just see here intersection B is basically intersection C. So you can write this is B union A intersection C. Just we are considering it as 1 and this is 2. So this is basically by 1. Okay. Now if we apply distributive law, so it will be B union A intersection B union C. So here I am applying distributive law, that will be B union A intersection B union C. And it is by distributive law. Now, with the help of commutative law, we can write B union A as A union B. And here is intersection B union C. Why? Since by commutative law, we can write A union B. This is basically exactly equal to B union. This is a commutative law in set theory. Now, here it is A union B, and that we can write here union B equals to A union C. So that we can write A union C intersection B union C. Since by 2, what is given? A union C, this is equals to A union B. So we can replace A union B by A union C. Now again we apply the distributive law. It will be A intersection B union C. So this is also by distributive law. What we have to show? We have to show this will be C. Okay. And in that case we will prove B equals to C. So A intersection B, that we can write again A intersection C union C. Why? We just see here by 1 A intersection B equals to intersection C. So since by 1, what we have seen A intersection B equals to intersection C. So again by absorptive law, what we can say intersection C union C, that will be C again. So what we have to prove starts from B, and where we have proved it is C. So B equals to C. and hence the proof is complete. Okay. Now we'll come to the next important problem. The problem is next problem, problem number 3. This problem is also very, very important for the B.Sc examination in Calcutta University, especially, and maybe in other university. Let A, comma B, comma C be subset, be subset, be subset of a universal set, capital U. Sometimes universals are represented by capital U or capital S. Then prove that, the question is, then prove that A symmetric difference C equals to B symmetric difference C, and that will imply A equals to B. That we have to prove. So here the universal set is basically U. So U is here the universal set, and A, B, C are the subset. Okay, so A, B, C are the subset of the universal set. So what is, if we try to solve it, the solution, what is exactly given? So given A, B, C are subsets of the universal set capital U. Previously the universal set is represented by S, now it is represented by capital U. And what is exactly given? It is given A symmetric difference C equals to B symmetric difference C. What we have to prove? Here we have to prove that A equals to B. That we have to prove. So here we will consider two cases. So we just take X belongs to A here. X belongs to A. Take an element X belongs to the set A. So here it is the universal set U, and this set is A, and we have taken element X belongs to A because here is a subset of the universal set. So we can take an element X belongs to A. So we shall consider two cases. So we consider two cases. Okay. So our first case, the case 1, we consider let X does not belongs to C. Okay. So then if X does not belongs to C, in that case X belongs to A minus C. Okay. So this set you consider C. If does not belongs to C, so X belongs to, obviously this is A minus C. X belongs to A minus C, as X belongs to A, but since X belongs to A and X does not belongs to C, so that implies X belongs to A minus C. And that implies X belongs to A minus C here, and A minus C is basically subset of A minus C union C minus C. Okay, because we just take one union of the other sets, it will be bigger than this A minus C set, and this is basically A in symmetric difference, but definition of the symmetric difference, and A symmetric difference C, and from the given condition this is basically B symmetric difference C. So we can write in position of A symmetric difference C, we can write B symmetric difference C. So that means here that implies X belongs to B symmetric difference C, and that implies X belongs to B minus C union C minus B. Now, since X does not belongs to C, we are in the case 1. In case 1, what is written? X does not belongs to C. Since X does not belongs to C, so X does not belongs to C minus B. Okay. And hence what we can say? So from 1 and 2, X belongs to B minus union C minus B, and here X does not belongs to C minus B. So therefore from 1 and 2, we say that X belongs to B minus C, and B minus C is also subset of B. So what we have proved? We proved here X belongs to B. So that means in the case 1, X does not belongs to C. That implies X belongs to B. That we have proved in case 1. Now we'll move to case 2. What is case 2? Now we'll move to, so this is a single star. Now we'll move to case 2. Case 2. So here we have taken a particular element in A, that is X. That X belongs to C or does not belongs to C. X does not belong to C. This is our case 1. So what should be case 2? So case 2 will be let X belongs to C. And in that case then X does not belongs to A minus C. Why X does not belongs to A minus C? Because since X belongs to A and X belongs to C, so if you see the Venn diagram like this is your A and this is your C, and X is here. X is intersection. So obviously X is not in A minus C. Okay. So the Venn diagram gives us this information, and that implies X does not belongs to A minus C, and A minus C is also subset of A minus C union C minus A. And this is basically definition of asymmetric differential. Okay, and asymmetric differential, this is given here. This is basically B symmetric differential. So here we can write B symmetric differential. Why? Because asymmetric differential equals to B symmetric differential. This is exactly given. So that means what we get here? X does not belongs to B symmetric differential. Okay. Now here, if possible let consider if possible let in that case, if possible let X does not belongs to B. That X belongs to C, and we just consider possible let. If possible let X does not belongs to C, what will happen in that case? So that means it implies X does not belongs to B minus C, and X also does not belongs to C minus B. It does not belongs to B minus C, but X belongs to C minus B. Why? Because since X belongs to C, that we considered in case 2. So that means what we can write here. So that means X belongs, since X belongs to C minus, that means X belongs to B minus C union C minus B. So that means B symmetric differential. So that implies X belongs to B symmetric differential, and that contradicts 3. 3X does not belongs to B in symmetric differential. Here we have proved X belongs to B symmetric differential. So which contradicts 3. So that means what we assume here, X does not belongs to B. This is not true. So in that case, we proved here X belongs to B. This is a double star. So in the both cases, what we have proved? If X does not belongs to C, then we have proved here X belongs to B, and here also if X belongs to C, then again we proved here X belongs to B. So combining case 1 and case 2, combining case 1 and case 2, what we conclude? We conclude that X belongs to B in the both cases. Now we have taken X belongs to A, and what we proved here? We proved here X belongs to B. So therefore, X belongs to A, that implies X belongs to B. And this information gives us a subset of B. Why a subset of B? Since X belongs to A is arbitrary. In similar way, you can prove this is triple star and this is by single star and double star. That considering as double star. Now in similar way, in similar manner, we also prove that we also proved that B is subset of A. So therefore, from triple star and what we conclude? We conclude that A equals to B. So that means our conclusion is if A symmetric difference B, what will be your conclusion? A symmetric difference C equals to B symmetric difference C, that implies A equals to B. So here the proof is done. Now we'll come to next question. Question number 4. Give a suitable example. Give a suitable example to show that only the condition A union B equals to A union C, or only A intersection B equals to A intersection C does not necessarily imply B equals to C. The question is how to prove. How to pick up the example by showing one example. Here you just see A intersection B equals to intersection C and union B equals to union C. Both togetherly we can show that B equals to C. But if you pick up the single condition, you can't show this is true. So that means we need to set up the example. So now we will come to the solution. Say we just consider the universal set here. Universal set is as S equals to say 1, 2, 3, 4. So this I am considering as universal set. And in that case we have two subset A equals to 1 and 2, and 3 subset B equals to 2 only, or say 3 only, and C equals to 2 and 3, and all are basically subset of the universal set. Then just you consider A union B. So this will be 1, 2, 3, and this is equals to A union C. So this condition is basically holds. Okay, but what is our observation? Our observation is here B not equals to C, because B is a singleton set, contains only 3, and C contains 2 elements. So our observation is B not equals to C. Again, so this is our example, first example 1. Next we produce another example, example 2. We take same universal set. Say our universal set is equals to again 1, 2, 3, 4. And here we consider A equals to 1, 2. Say your B equals to 2, 4. And C equals to 2, 3. All are subset of S. In that case, A intersection B, this is basically singleton set 2. And this is also equal to B intersection C. But our observation is here B not equals to C, because B contains element 4 but C does not contain the element 4. So B and C are not equal. So by showing this example, we proved that we showed here only a single condition, either union B equals to union C, or the single condition intersection B equals to intersection C, that does not necessarily imply B equals to C. Now we'll solve next important problem. Okay, state true or false with justification. Question 5. State true or false with justification. How to prove state true or false with justification? A minus B, that complement, that you will say it will be true or not. If it is true, you need to prove it. If it is false, you need to set up one counter example. A minus B complement equals to B minus A complement. So here the solution is, the result is false. The result A minus B complement, this is equals to B minus A complement. So the result for any two set A minus B complement equals to B minus A complement, this result is false. Why it is false? We need justification. So what will be our justification? This result is false. So we just consider, take an universal set, capital S equals to 1, 2, 3, 4. This is our universal set. We have considered two subsets is here, A equals to 1, 2 and B equals to 2, 3. This is subset of S. Then you just check here. So here universal set is contains 1, 2, 3, 4. A is basically 1, 2 and B is 2, 3 and 4 is here. So this is your A and this is your B. So then what will be A minus B? So A minus B will be that part. That means 1. Now we are taking the complement on both sides. If we take the complement, one complement, that will be S minus singleton set 1. So that means it will be 2, 3, 4. Whereas B minus A, what will be that set? B minus A will be 3 only. If you take the complement on both sides, it will be S minus singleton set 3 and that will be 1, 2, 4. So what we observed? So we observed that in that case A minus B complement not equals to B minus A complement. Okay. So here the statement is false. That is justified with this help of this particular example. Now we come to next important problem. Problem number 6. Let A, B, C be subset of a universal set. The subsets of a universal set capital S such that A union B equals to A union C and A complement union B equals to A complement union C, then prove that B equals to C. Now the question is how to prove this kind of problem. First you try to identify what is the given, what are the given condition and what we have to prove. So here it is given A, B, C are subsets of the universal set capital S. And again the condition is A union B equals to A union C and A complement union B equals to A complement union C. What we have to prove? So we have to prove that this is our work to prove B equals to C. Okay. So now start from the set B and we'll prove that it is equal to C. So now start from B and that we can write phi union B. Why? Because the empty set is basically subset of any set, it will be subset of B. And that element phi we can write A intersection A complement. This is this union B, since A intersection A complement, this is basically phi. So that will be A. If we apply the distributive law, it will be A intersection B union A complement intersection B. So this is by distributive law. And that will be here A intersection B is, so okay, it will be A union B. If we apply the distributive union B, that will be intersection A complement union B. Okay. So that will be A union B if we apply distributive law, intersection A complement union B. This is our distributive. Now what we have to write here, A union B, that we can write A union C, and A complement union B, that we can write A complement union C. Just I am given this equation is 1, so you can write it by using 1. So again we apply here the distributive law. So what we will get? We will get here A intersection A complement union C. And again intersection A complement, that will be phi union C as an empty set, and that will be C. So what we have proved here? So therefore we have proved here B equals to C. And here our proof is done. Thank you so much. In the next class we will solve the many other important problems in set theory.